Welcome back to another video. So today I want to talk about similar triangles, which is a topic that comes up very frequently. Now, many students tend to have trouble with similar triangles, but hopefully after this video, this is just part one of a 4-part series, by the way. So there are many more videos to come for this topic, but hopefully after those 4 videos, you will be much more comfortable with similar triangles. We're going to go over everything. We're going to learn how to identify similar triangles, how to set up your ratios, and solve for what you're looking for. And then in the end, we're going to go over some proofs as a little bonus. Okay? Because you cannot escape the proofs for similar triangles as well. Sorry about that. Anyways, let's talk about similar triangles. So first, we're going to go over a similar figure in general. Now, similar figures must have the same shape, but they may have different sizes or orientation. Okay, so that's a similar figure. So basically, one figure is simply just a blown up and possibly rotated or flipped version of the other. Now, that's similar figures in general, but as I said before, special focus will be on similar triangles because triangles are the fundamental shape. So that's what we're going to be looking at today. As you can see in this diagram up above, we have 2 triangles, and these 2 triangles are actually similar to each other. And we're going to show how to prove that later on. But you can see they do have the same shape. They're just a different size. So this one over here is basically just a bigger version of this smaller triangle over here. And it did not have to be orientated this way. If it was like this as well, that's still a similar triangle. You know, these 2 triangles are still similar to each other. It's just facing a different way, but the point still stands. They are similar. Great. And over here we have a more specific example with some numbers, because why not? So over here we've labeled some angles. Remember, this little square over here just means it's a right angle, so it's 90 degrees. And both of these triangles have measurements of 55 degrees and 35 degrees. And we're going to see later on, these 2 triangles are definitely similar to each other. So that's worth noting as well. These 2 triangles are similar to each other. And again, just to show you, as you can see, if we just took this one and just orientated like this, maybe that's a little easier for you to see. So next, we're going to go over some properties of similar triangles. And this is very important to remember. So when 2 triangles are similar, all corresponding angles are equal, and all corresponding sides are in a constant ratio. So in other words, they're proportional. Now, if you're confused on what that means, I'm going to show you what corresponding means in just a second. So this is our notation that you're going to use. So whenever you want to say 2 triangles are similar to each other, you're going to use this little squiggly line. So whenever you see this single squiggly line, that means similarity. And we read this out loud as is similar to. So in this example, over here we have triangle ABC is similar to triangle XYZ. And so this is what I meant by corresponding. So in these 2 triangles, angle A is equal to angle X. So that's why we wrote it first. So A corresponds to X. Angle B equals angle Y. So that's why we wrote it second. B corresponds with Y. So basically B in this triangle corresponds with Y in this triangle. So that's what we mean by corresponding angles and corresponding sides. And of course, last but not least, angle C is equal to angle Z. So this angle here, it might be right, we don't know, but basically angle C is equal to angle Z. So that's why we wrote it like triangle A, B, C. So first A, then B, then C, therefore first X, then Y, and then Z. So you can think of it as going around with these little arrows, okay? A, B, C to X, Y, Z. Notice, it is not A, B, C to Z, Y, X. And we're going to see how that can mess things up. So it's very important to write the order of the similarity properly. So that means writing our corresponding vertices with each other correctly. A with X, B with Y, C with Z. If I'm putting a lot of emphasis on that right now, that's because it's very important that you get this correct, because this similarity setup over here is how you're going to set up your ratios later on. And speaking of ratios, actually, over here. So this is what I meant by corresponding sides are in a constant ratio, so they're proportional. So basically AB, if you take this side AB over XY, you take BC over YZ, and you take CA over ZX, well then, this actually turns out to be, since it says constant ratio, this turns out to be the same number. Alright, so that's a cool, neat little fact. Excellent. Alright, now I want you to keep these two properties in mind, because now we are going to go over to something else. Very, very important. So pay special attention to this section, because you're going to be using this a lot. So there's no escaping this. This is probably what your teacher wants you to do. Let's go over tests for similar triangles. So basically, this is how we're going to show that two triangles are similar without a doubt. They are 100% similar. So basically, in other words, we're basically proving two triangles are similar with these three tests. Now, there are many methods to prove two triangles are similar, since we cannot just say, unfortunately, these two triangles look similar, therefore they are, which is kind of what we've been doing so far. I sort of just, these two triangles over here, well, they kind of look the same, right? They look similar, but now we have three rigorous tests to show that it is indeed similar. And they are called as follows: AA, SAS, SSS. So these are their acronyms. And I'm going to put special emphasis on AA over here, because this one is probably the most important / common. So it pops up the most frequently. That doesn't mean the other two tests are not important and you should forget about them. It's just that AA probably comes up the most often. And it tends to be the easier one in general. So if we like easy ones and important ones and frequently popping up ones. So that's what AA similarity is. Now you're probably wondering, what do these even mean? I said they were acronyms for something. Let's take a closer look. First up, angle, angle, similarity. So that's what AA stands for. Now, as we can see by the name, angle, angle similarity basically just says that if we have two triangles which share two angles in common with each other, then the triangles are similar. And that's all we need. All we need are two angles. We don't really need to say specifically that the third angle is the same because that's already implied. Because they're both triangles, they're going to add up to 180 degrees. So if we find two angles which are the same, well then automatically that third angle is the same as well. So it would be a little redundant to say angle, angle, angle similarity. 2 is sufficient enough to prove similarity. So as we can see, in this example, angle A, so this one over here, equals angle D. And angle B equals angle E. How do I know that? Well, as we can see, this little tick over here, this little green tick, indicates that angle B is equal to angle E. Now together, this implies triangle ABC is similar to triangle DEF. And again, notice that we're lining this up properly. Angle A is equal to angle D, therefore we write it first. Angle B is equal to angle E, therefore we write it next. And then automatically what's left is C and F. And as we said before, corresponding sides are in a constant ratio, so if we take side AB over DE, side AC over DF, side BC over side EF, as I said before, that's going to be the same number. So whatever that turns out to be. And very, very important, note, I said this before, but it's worth saying again. Notice that we do not say, so this is incorrect. So if you said triangle ABC in this diagram is similar to triangle DFE, that would actually be incorrect. That is not the same. Make sure you see this. This is not saying the same thing as this. Let's take a look why. So, okay, this ABC is still the same, but did you know that DEF is different than DFE, at least when it comes to similarity? Because yes, they technically are the same triangle, the triangle with vertices D, E, and F, but the order matters in similarity. Always. Always remember that. Order matters in similarity, especially when you write out a similarity relationship. So why is this incorrect? Well, let's say if this was correct, that would say, okay, angle A is equal to angle D. That is correct. So that's not wrong. The problem is the next letters, right? This says angle B is equal to angle F. Well, we know angle B is equal to angle E, not angle F. So that's why this is wrong. And the reason, here it is, the reason why it's so important to get your similarity relationship right from the get-go is because if it's not, what you would do is you would actually write out your ratio of sides like this. AB over DF equal to AC over DE. And that is not necessarily true. It could be true, maybe by luck, but then you would get the answer by luck. It's not always true though. However, this will always be true. So do you want to get lucky or do you want to get it right properly? Okay? Worth noting. So remember, please remember, order matters in similarity. And the whole idea is to just be consistent, basically. So you need to write this angle matching with this angle matching with this angle. If you do that, there's no way you can screw this up. So that's angle-angle similarity taken care of. And by the way, we're going to see later on how to get this ratio, because I know this is a question many students have, how to set up this ratio perfectly correct every single time, even if you don't have a diagram. So let's say you don't have a diagram in front of you. Let's say you just have this equation. Well, you can set this up very easily all the time. So if you're confused on how I'm getting this right now, don't be. We're going to cover that in the future. Actually, later on in this document. So that's coming up. No need to worry about that. For now, we need to take care of method number 2, which is SAS similarity. Now, SAS is the acronym for side, angle, side similarity. So for these similarities, whenever you see S, that stands for side, A means angle. So you could probably guess what SSS similarity is, but we're going to get to that later. For now, let's talk about side, angle, side. So side, angle, side similarity states that if two pairs of corresponding sides of two triangles are proportional and the included angles are equal, then the two triangles are similar. Okay, I'd say it's a lot easier to look at it with an example because that was a mouthful. So basically, we have these two triangles over here. And what do we notice? Well, first of all, we're given two side lengths, so that's where the side and the side comes in. So two side lengths. And then what else are we given? We're given an angle of 50 degrees for both of them, and this 50 degrees is in between these two sides. So side, angle, side. Okay, the angle's not here, the angle is not here, the angle's in the middle. So side, angle, side. An interesting fact about these numbers, we can see that 6 over 3 is equal to 4 over 2. When you do the math, it ends up being a ratio of 2. So side AB over side XY equals side AC over XZ. And this included angle, so this angle in between the two sides, is equal. Then we say triangle ABC is similar to triangle XYZ. All right? So that's side, angle, side similarity. And last but not least, SSS similarity. And don't worry, we're going to get a lot of practice with these three methods. Right now, I'm just going over them very briefly. So you're going to get a lot of practice. Anyways, if you guessed that SSS stands for side, 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 you would be correct. Let's talk about side, side, side similarity. Now, side, side, side is like angle, angle, very easy to identify because in this case, there would be no angles given. So it's just three sides. So you're given three side lengths. And if the corresponding sides of these two triangles are proportional, then the two triangles are similar. Basically, if you take AB, which is 14, and you divide that by XY, which is 7, you get 2. If you take BC, divide that by YZ, that's 8 over 4, that's also 2. You take AC, divide that by XZ, 10 over 5, that's also 2. Well, guess what? These three ratios are exactly the same. Therefore, we have triangle ABC is similar to triangle XYZ. And that's side, side, side similarity. So those are the three methods that I want you to keep in mind. Angle, angle, side, angle, side, 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 side. I'd say the hardest one of the three for most students to remember is probably side, angle, side, because we're mixing and matching both sides and angles. Whereas, in AA, it's just angles. In side, it's just sides. But the one that mixes both sides and angles tends to mess a lot of people up. Okay, now as promised, I'm going to help you to write out similarity relationships. So basically those ratios you saw earlier, I'm going to show you how to write them out properly 100% of the time, every single time. So pay special attention to this section. I feel like I've been saying that the whole video. You should pay special attention to every single thing I'm saying, but especially for this one too, because then there's no way you can mess up your ratios ever again, okay? So if you're in a situation where you're messing up your ratios and you're frustrated, after this, should be no more problem. Now, the great thing about math is we can think about things, the same things, in different ways. And in this case, we can write out similarity relationships multiple different ways. So there's not just, I don't want you to just think there's only one correct way to write out my ratios. Actually, the great thing is you can write it out many different ways. And in this case, I'm going to show you. So over here, we have two triangles here. I'm going to show you how you can write out the ratios in two different ways, and both of them would still be correct. The main idea, though, is as long as you're being consistent, it doesn't matter how you write out the ratios. As long as you're consistent, it will be correct. All right, let's take a look. So in this diagram, we have triangle ABC is similar to triangle XYZ. And just as a little bonus, for those of you paying attention, how do we know this? Well, we have, as you can see, a side, an angle, which is equal to each other because of this tick, and another side. Since this angle is in between the sides, we have SAS similarity. Indeed, 15 divided by 5 is equal to 9 divided by 3. Now, from here, we can write out the ratio. So I said 15 over 5 was equal to 9 over 3. So that would be taking side AB, which is 15, over side XY. That is equal to AC over XZ. But guess what? Instead of going back and forth between these two triangles, let's see what happens when we take AB. Let's just look at within that triangle. Let's compare it to side AC. So we take that 15 and we divide it by 9. That will give you a ratio of 5 over 3. 5 over 3, does that sound familiar? Why don't you look over here? 5 and 3. So AB over AC is equal to XY over XZ. And notice how even though these two ratios may look different, they're actually saying the same thing, and they're both correct. Now, I promised you that we would be able to get these ratios even if this picture actually wasn't here. So let's consider that. Let's just pretend this picture isn't even here. I'm showing you a little preview of the next page, but let's stay over here. How would we go from here to here? Well, I emphasized consistency for a reason. So let's see, to get this first ratio, if we're just given these letters, what I would do is I want you to start thinking in terms of like groups. So if we take these first two letters, AB, and we take these two letters, XY, then we get AB over XY. Then what we would do is let's pretend this B isn't even here. We end up with AC, And let's pretend this y isn't even here. We end up with xz. And that's how you get AC over xz. And this method will always work. Trust me. What we can do next, how do we get this ratio over here? Well, let's say we took AB, and then let's say now we take the first and the third, AC. That's how we get AB over AC. Since we took the first two letters here, we need to take the first two letters here, XY. Since we took the first and the third letters here, we need to take the first and the third letters here, XZ. And that's how we get this ratio, XY over XZ. So basically, it's a lot of what you can do is you can even cover this up with your finger. Like you can pretend this is your finger and you're putting it right over the B, so it's gone, and then you end up with AC. Then you would have to put your finger above the Y, the middle letter, because you put your finger above the middle letter here, and you end up with XZ. And you keep doing this. You can imagine putting your finger over the Z, you end up with XY. You put your finger above the C, you end up with AB. So the whole idea is to just be consistent. So these two top numbers came from covering the last letter, and these two came from covering the middle letter. And as long as you do this, it will always 100% work. So as a little practice, why don't you try covering up maybe the first letter, A and X. So now you use B, C, and Y, Z, and try to write another ratio yourself. So as I said before, it is very important we get the vertex order right when establishing the similarity relationship. So the vertex order is basically just how we write out. So here, vertices A, B, C, X, Y, Z. Because you can imagine, with that method I showed you before, imagine if your vertices were labeled a little differently. Let's say they were labeled like triangle ABC, and let's say you switched around the order. Let's say maybe X, Z, Y. Well then, without a picture, if you just do the covering up method, so let's say we cover C and Y, well now you're getting a completely different ratio. You're getting you're getting a ratio involving AB and XZ, not XY. And then maybe you would set that equal to, let's say we cover up the middle letter of each now, so covering up B and Z, then we would get something like this. And if you think that these two are the same, think again, because they are not. So basically, if you get this wrong, you're going to end up with something completely different. So that's why I emphasize the importance of always getting your vertex order right. And the easiest way to get your vertex order right is to just, as I said before, imagine you have arrows and you're going along this way. Then you have to start from here and go along this way. Please do not change the direction. All right, enough theory. Whew, that was a little long. Let's get some practice. But that theory was very, very important because now we can get into the problems. So we're going to use everything we've learned. So I believe we have 5 or 6 problems where we have to identify which similarity method is best to use. So that's another reason why I want you to get that practice. When you see certain setups, your mind is going to learn, okay, maybe this is involving side angle side. Maybe it's involving angle, angle. Maybe it's involving side, side, side. And you're going to get better at this the more you practice. Okay, so for the following, state the similarity relationship. So that would basically just be the ratios and what kind of similarity is involved. So you're going to get a lot of practice with this in your homework as well, and I'm going to show you right now. This is how I want you to do it. So I don't think I've given myself much space, so I'm guessing maybe it won't be that long. I'm not sure. I haven't actually written the answers off to the side right now, so I'm doing this for the first time with you guys as well. Normally I write down the correct answers to the side. I did not do that this time, so we have to do it now. A little scary, but I think we can do it. Okay, so over here we have two triangles, and what are we given? Are we given any sides? No side lengths, so automatically we can't use these. So basically it's already AA similarities involved. And as we can see, indeed, two angles are given. We have one 50 degree and one 60 degree. And guess what? We have one 50 degree and another 60 degree. So let's see how we can write this out properly. In this case, we start with triangle ABC. Let's go in any order. We can go any order for the first triangle, but then the second triangle is determined by the first. So angle A is 50 degrees, angle D is 50 degrees, that means D has to come first. Now, next question, is it going to be E or F that comes next? If you answered E, I'm sorry, that's incorrect. So it looks like this one switched up a little. It's not in alphabetical order. Angle B is 60 degrees, angle F is 60 degrees, so therefore F must come next. And then by default, E is left. So this is how we would write it. Triangle ABC is similar to triangle DFE by, I'm not sure if I'm going to switch the colors every time, but you can say by AA similarity. And that's good enough for me. You don't need to write out fully angle similarity. If you say AA, I know you know it's angle. Okay, now I think in fact that's all we are asked to do. So in fact, you don't have to write out the ratios. You could, if you want practice, you could write out the ratios for yourself. Okay, so again, pretend you're covering up maybe the last letter, and then you're covering up maybe the first letter. So you could get that practice by yourself, but for now, I think this should just be good enough, since that's all we're asked to do. So perhaps that's why I gave myself so little space. It looks like this is not going to take up a lot of space. Question 2. Okay, question 2. Now question 2 has only side lengths. So we're given 4, 2, and 3, a side length of 6, 3, and 4.5. So we know we have SSS similarity going on. Automatically get that out of the way. This is SSS similarity. Now, how are we going to decide the order which we write this relationship? So this one might be a little bit trickier because of this nasty 0.5. So the way you're going to do this, in fact, for all side similarity triangles, you need to figure out, because we write it based on how these sides are related to each other, you need to find out basically how these sides are, how the sides of, let's say, this triangle are related to the sides of this triangle. Now, it may not be immediately obvious, so the way I like to start is compare the smallest number for each triangle. So pretend these aren't even here for now. How is 2 related to 3? So it might be a little funny if you're not used to this type of maneuver, but BC, sorry, wrong way. I meant QR, which is 3, is equal to 3 over 2 of BC. Because 3 is equal to 3 over 2 times 2. So this might look a little awkward at first, but when you see it's just basic cancellation. So this is indeed equivalent to each other. So basically you take side length BC, multiply it by 3 over 2, and you get 3. So to someone with not as much experience, it might look a little funny. So that's why experience is very, very important. You need to see these sort of weird types of manipulations. But you'll get used to it very, very quickly. Now let's see, does this hold? That's the question. Does this hold for our other sides? Let's compare, let's say, the biggest side. 4 and 6. Just trying to avoid this decimal until we cannot avoid it any longer. So anyways, is 6. So is 6 equal to 4 times 3 over 2? You can get out your calculator, but you'll find out it actually is. And now, last but not least, is 4.5 equal to 3 times 3 over 2? Again, you'll find it actually is. So basically, the side lengths of this bigger triangle are 3 over 2. I know that sounds funny, but it's 3 over 2 times the side of each corresponding side of the original triangle. So like this original triangle, this triangle over here. So 2 times 3 over 2 gets you to 3. 3 times 3 over 2 gets you to 4.5. 4 times 3 over 2 gets you to 6. So indeed, there is a good, nice relationship between these two triangles. Therefore, we can write, doesn't really matter, you don't have to go alphabetically. Let's say maybe we went like this time, triangle BCA, as long as you write it correctly for the second triangle. So the way we do this, if there's no angles, notice BC is the smallest side too. So the smallest side would be here, QR. And then automatically P is left. And just to verify if this is correct, let's see. So CA is the second largest side. So is RP the largest side? No, it is not. In fact, it is actually the largest side, not the second largest side. Sorry. So this is actually incorrect. So we can go ahead and fix it. So that's why it's always good to check. We can fix it like this. Now we can check. So BC is still the shortest side. RQ is the shortest side now. CA is the middle side. PQ is indeed the middle side. And let's pretend this C isn't there. AB is the largest side. And PR is indeed the longest side. I'm sorry, now that I think about it, I'm looking at this, and this side looks like it was supposed to be the 6, just visually. So I think I'm looking at this now. It just looks a little funny. Yeah, I think this side was meant to be the 6, and this side was meant to be the 4.5. Anyways, I think that is my fault. So I think that's why maybe it looked a little bit weird. But anyways, let's just roll with this, even though it doesn't look correct. Because, I mean, you can't always just go by images for geometry. They will not always be drawn to scale. Let's just go with this. Anyways, kind of a weird one. Okay, question 3. Okay, this one is a little bit amusing. If you're looking at this one and saying, I have nothing, I'm a little bit disappointed because you actually do have something. You have many things, many useful things. So this is why experience, as I said, is so important in geometry. You got to train your eye to see things that aren't there, or you need to train your eye to see things that are there but aren't exactly obvious. It's not labeled explicitly for you, but it's still there. See these little these little ticks? Remember what that means? Yes, these two lines over here, they're parallel. And what do we know about parallel lines? Well, if you remember your little Z pattern, you remember something called corresponding angles. So guess what? According to these parallel lines, this angle is actually equal to this angle. What else do we have? Let's see, let's use a different color. This angle is also equal to this angle. And there we go. So the two Z patterns are like this, and there's also one that goes like this. So guess what? We have two equal angles. So this is actually a similarity. Two angles, good enough for me. Let's write this out properly. So triangle ABC. Let's say we go in alphabetical order. So A, we said it's marked with this little blue angle, so in fact it should be E that comes first. B is orange, so D comes next, and C is shared between both of them. Clearly, A, B, C, E, D, C. So they both share the vertex C. And I believe I already wrote this out, so we can just copy and paste that. Excellent. So I think I gave myself a little bit more space to mention something very important to you that I want you to always remember, not just for similar triangles. You're going to see this come up over and over again in geometry. It's probably one of the most important facts of Euclidean geometry. And I'm going to write it out. It can be summarized in one sentence. I don't like that N. So when you see parallel lines, I don't want you to just give up. I want you to be excited, because guess what? You have equal angles given to you. I feel like I should be boxing this one. I probably will go and edit this later on in the solutions document. I'm going to put like a big box and like some asterisks and like just a lot of emphasis on this point because it is worth remembering. Question number 4. I would say this one is probably the trickiest of the bunch. Give you a minute to think about this one. This one is tricky. I don't blame you if you're confused right now. So question 4. It seems like we have a side length, another side length, and another side length. But we're not given any angles. There's nothing marked in this diagram. And you're thinking maybe there's no side here, there's no side here. So it doesn't really look like the typical setup that we saw before. It doesn't look like anything. It doesn't look like angle, angle. It doesn't look like side, side, side. We do have 3 sides, but they don't make a triangle. They just sort of make this weird, well, it almost looks like an inequality sign, but like a large inequality sign. Anyways, it doesn't look like side, side, side. So what could it be? Could it be side, angle, side? Again, to those inexperienced, you might say no. But to someone with a sharp eye, this is why practice is so important. This actually is side, angle, side. I know, that just like blows your mind. You're like, what? Side, angle, side? I don't see any side, angle, side going on. There is. This is side, angle, side. If you'll notice, if I take, and this is where your sort of mathematical intuition has to kick in. You need to consider how numbers are related to each other. Did you know that 4 over 6 is equal to 6 over 9? You might be looking at that and saying, yeah, duh, it is. But where is this 9 coming from? How do we make 9? You take 4 and 5, 4 and 5, and add them together. Okay? There we go. So 4 over 6 is equal to 6 over 9. So there's our sides. I promised you a side, angle, side. So where's the angle? Over here. This is where the angle is. You'll notice we have, in this first triangle, side, angle, side. I'm talking about triangle ABD. Now, pretend this isn't here. I want you to look at the bigger picture. What do you have? You have a side, an angle, and a side. Oh, okay. There we go. We've solved it. Now we see the side, angle, side. So this one can be in any order, but I'm trying to go, let's go DAB. So DAB, so DA is the 4, and AB is the 6, which means the 6 has to go on top. So AB has to come first and to complete the triangle with C. Let's see, does that make sense? So we can check DA, 4 over AB, 6 equals AB, 6 over BC. That is not correct, which means we actually need to fix this. See, so this is why it's always good to fix. I believe it should be swapped around then. BAC. Now, does this make sense? Triangle DAB. So DA over AB is equal to BA, AB, same thing, over AC. Indeed it is. And I know I said order matters, so if you're confused on why I said AB and BA are the same, well, in this similarity relationship, we have to write them out in this order, but when you're saying the actual length is not changing, they're both 6. So that's why I consider them to be the same. So this one was a little tricky to see. Let's see, did I have side, angle, side? I'm gonna just copy and paste that. There we go. And I believe this is the last. Oh, nope, there's one more. Okay, so we have 6, not 5. All right. Now, here we go. Again, not given much, but we can still solve this problem. So, what do we see? Hey, there's our friend again from question 3, I believe. Yes. More parallel lines. And also, so this is what I mean by looking at the bigger picture in geometry. So this is a good topic to cover, I feel, because like similar triangles in general, they're going to help you a lot with your overall geometry. So I see 2 triangles. I see this one, and I also see this bigger one over here. And did you know that they share this angle? So we have a shared angle, but what else do we have? Well, because these lines are parallel, so both of these lines are parallel and they're hitting this line over here, okay? We know that these, hang on, orange. We know that these angles are equal as well. And there we go. We found our 2 angles. So these 2 angles in this triangle and these 2 angles in this bigger triangle. You can almost pretend that HK isn't even there. So let's write it out. Triangle HBK is similar to, so H did not have an angle, so we can say we're going to start with A, and B is involved in both of them, so both of these triangles share vertex B and C, and we can say by a similarity. Again, if you're at home, I want you to write out these similarity relationships. So write out your ratios. So set them up. HB over AB is equal to BK over BC, something like that. So I think that's why I gave myself so much space over here, but we're not going to do that right now. I'm going to leave that for you to do as practice. We're just going to get this first step out of the way. But don't worry, in the solution document, I think I will fill those in for you if you want to see it. But don't worry, we're going to get a lot of practice with this. And trust me, in the problems that come, we're not just going to write this out, we're actually going to solve for some sidelines. Because as you'll see in the problems, you're going to be given some numbers and you're going to have to find something. So this first video is mainly just being used to write out this first step properly. That's my whole goal for this video. If you can do that, congratulations, you have succeeded. That's all I want from this. Final question, and then we're done. You can get out of here. Okay. This one is a little bit trickier as well. Okay, so because we have, well, we got 4 numbers this time. Wonder what that's about. And now we have, when people look at these, notice how in the previous problems, I tell you if they're parallel with these ticks, okay? That means they are, without a doubt, parallel. Now, if you don't see ticks, I don't want you to assume that they're parallel. So I don't want you to assume, oh, well, these 2 are parallel, because they may or may not be, okay? So that's, I think, where it gets a little tricky. People assume things are parallel when they may not be. So if it's not explicitly stated, I don't want you to assume. So let's assume maybe they're not. They could be, but for argument's sake, let's just pretend that they're not. Okay, like we're not guaranteed to be parallel. How would we go about this? I hope by now you're starting to see a pattern of how we can look at the bigger picture. Because if we do that, this angle is common to both of the triangles I just showed you right now. And we have side, angle, side, side, bigger side, angle, bigger side. So this is side, angle, side as well. So let's write this relationship out properly. Triangle, let's start with the smaller one. EAD is similar to triangle CAB by SAS. And actually what I did was not good, actually, sorry. What we should do is we should always check and make sure that the ratios of corresponding sides are equal. So 8 over 5 is 8 over 5 equal to 32 over 20? You'll find it is. So you should have done that first and then write this out. And let's see if this is correct. Yes, you should have verified that first. That's what I meant. EA, so that's 5 over AD, this 8. Is that equal to CA over AB? 20 over 32. It is indeed. This angle A is being shared in the middle, so this is correct. And there we go. That's all there is to this first video. So we went through a lot. We learned how to identify similar triangles and prove that two triangles are similar with three common techniques: angle, angle, side, 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 and we got a few practice problems in. Now, as I said before, if it seems annoying right now that I'm spending so much time going over this, what seems like very basic and annoying, tedious work, trust me, this is very important. That's why we're spending so much time on it. I know we want to get to the fun stuff, which is more challenging problems, but if you can't master this first step, you have no hope for the problems that follow. I don't say that to scare you. I say that to really emphasize why this is so important. So please pay attention to this, do all the homework that I'm about to give you, and then go on to video number 2. Video number 2 will be slightly harder. Videos 3 and 4, those will be hard. Those will be challenging. So it all builds from this first video. That's why it's so important. If you walk into my future videos feeling, very iffy about this first video, that's not good. That's not what I want. I want you to first be 100% confident with this video. You need to be a master at it. You need to be quick. You need to be good before you watch the other videos. Otherwise, it's not going to make much sense. All right, so you have 3 problems. The first one is a true-false one. So I've given you 3 statements, and some are true, some are false. So tell me which ones and justify. So this one is really focused. I mean, I've given you a picture here to help you, but let's say even if you didn't have that, if you just had this is just to really help you write out these ratios properly. Question number 2. Question number 2 doesn't even have a picture, actually. So this one is really going to test your ability to set up the ratios properly without a diagram, because you won't always be given a diagram in geometry. Most of the times you will be, but not always. And then question 3 is very similar to what we did at the end in class, just some more challenging problems. So for each of the following, name with reason, and when I say with reason, it means one of the 3 methods. So say either by AA, SAS, or SSS, and then just write me a pair of similar triangles. So we have a few problems that look like this. This, parallel lines. Over here, more parallel lines here, and that's it actually. Okay, so with that out of the way, this has been Similar Triangles Part 1. So do the homework, and I will see you hopefully in Similar Triangles Part 2. Have fun!